Hi, so let's jump straight into the action. This time I don't have epoxy, so I'm going to use hot melt glue. This is probably a very stupid idea, but I really can't wait to test this. These hot glue guns are pretty crappy, as they have very low power and you cannot melt a lot of glue in one shot. So I'm using torch to melt it, but that will create a lot of fumes. I found hot air gun to work very well for this. The problem with hot glue is that it shrinks while cooling. So the final piece may not actually be as you desire it. And also it's quite flexible at room temperature. And it's ugly. That's the worst thing. I'm going to use washers to offset my rotor plates because nuts are wobbly for some reason. Just keep bearing seal ring clean if you use washers. Now attach the plates and be sure that they can rotate freely. Actually, I am pretty impressed how little problems I have with this flexible rotor, but don't get me wrong, I'm not saying that it's anyhow good. And here comes the tricky part. Watch out your fingers. Okay, shall we test this? Sure. You still have to give it a little push to start rotating. I tried all possible settings, but without any success. Now the power supply is limiting the current. And ladies and gentlemen, we have reached the terminal velocity. Okay, so before we will continue, I got some older stators I have tested. So this one is pretty chunky, but I accidentally offset the coils by 60 degrees instead of 120. Strange thing is that it works and actually is quite efficient. Now this one in contrast is super slim. It has only 4 turns of wire. Now offset is correct, and response of this coil was really impressive, but a lot of power was wasted in MOSFETs, otherwise it was quite good. Here you can see the difference between these two stators. And here's the one that was used in previous videos. Anyway, in the background you can see my new motor turning slowly. I want to see how slow it can go without losing feedback. Yep, it can go very slow. Since I want to use Hall sensors for servo variation, it doesn't really matter, but it's good to know. Okay, let's look at some debugging. As I don't have a scope, I once again use LEDs and slow down footage of the motor. So each pair of LEDs represents one phase. Polarity is determined by which LED of that pair is lit. It's quite clear that frequency is too high for the rotor speed. Now with my second version I overlaid video over this photo. I tweaked the contrast of the LEDs and placed a few labels here. Ha! Can your scope do this? And measurement time. So if you are interested in how to calculate the output power, link to my older video should appear on the screen or it will be in description. And I'm not going to do calculations now. So I'm claiming 80% efficiency. And if you do a math on numbers shown, you will get numbers from 20 to almost 70%. So where did you get this 80%? Did you suck it out of your thumb? Well, kinda. To be more specific, I am interested only in stator efficiency. If you are familiar with this setup, you can tell that it's not extremely precise, so there is some room for error. Also, I'm using block of aluminium to convert rotary magnetic field into static pressure, and that conversion is quite lossy. Actually, you can see this device as a mechanical induction cooker. I found that when I am reading about 1.5 newtons, the temperature of that block is about 40 degrees Celsius. Luckily I have identical block that I can place on the other side of the motor to have similar airflow conditions. I'm not going to repeat this sentence. Then I can place dummy load on it and compare the temperature. I did a comparison by simply touching the block, so there is no accuracy here, and I'm quite happy with that. But that's not the worst thing I did. I assumed that I have lost 1 watt in transferring vibrations to the table, and also I added power loss on speed controller to the efficiency. Well, I think this is called slightly biased educated guess. So let's look at the numbers, shall we? So I made a few measurements. Well, majority of these are made on earlier versions of the motor. We are interested in this graph, which corresponds to this range. The red line represents RPM divided by 10, and the blue line is measured efficiency. The highest efficiency was measured on this line. So I measured 66%. Below that line is the same measurement, but power output is corrected. I added 3.4 watts in total, of which 2.1 watt is thermal loss on magnetic torque converter, 0.3 watts loss is estimated on ESC, and 1 watt is estimation of rotor imbalance cost loss. Probably I should have completely omitted ESC loss there, but look at the nice numbers there. I simply could not resist. Now this is the lowest efficiency that I measured. This was on slowest speed possible with light load. And right below is the worst power loss measured. This is mainly due to heat loss on torque converter, and ESC was also quite hot. As you can see, line below has the same RPM but smaller load, and the power loss is smaller, but efficiency also, which is quite interesting. So in conclusion, I am really happy with the outcome of this experiment, and I hope that this was useful for you, and yeah, thanks for watching, and keep inventing.